All right, folks, let's start. This is Dr. Yuzo on ECE 318, Electronic Circuit 1. And can you guys hear me?
Yep.
All right, thank you, Shane, and we'll move on. So first of all, we need to review a little bit the last lecture. The most important thing from the last lecture was how to identify the channel, right? N channel or P channel for the given MOSFET, because the given MOSFET circuit might contains more MOSFET in any orientation. So we need to be able to correctly identify this N channel and P channel, and accordingly to have the equations. Yeah, because you can imagine N channel and P channel equations are different. Okay, they are different, and the different parameters too. And also, second one you need to identify correctly is the terminal, of course. Okay. So we have gate, drain, and source, right? And how to identify them. So first, the N channel, P channel means you're seeing the arrow direction, right? Yeah, N channel means your arrow is from the gate pointing towards the source, like this, and this, right? So this means N channel. Otherwise, it's a P channel. Okay? Is obviously the arrow is the indication of the current direction, and the N channel current is flowing from the drain towards gate and from gate towards source. Okay, it's such kind of current direction, or say from the drain towards the source. The P channel MOSFET has the reversed current direction. Okay. And to the terminal, the gate is fairly easy to be identified. However, the drain and the source, the difference is the terminal who has the arrow on it, no matter its direction. Okay, that terminal is the source. Okay, you have the arrow on that terminal. That terminal is the source, and then the other terminal is obviously is the drain. Okay, this is the identify the terminals and the channels. Okay, based on these, we can go ahead to talk about the DC analysis actually. So before anything, we need to once again review actually the concept of DC and AC analysis, okay? Because we have been doing those for the diode circuits too. The basic idea and the principle remain same here. First of all, why conducting both DC and AC analysis? The reason is very simple, because in the circuit, in transistor circuit, or say, you're gonna have DC supply or DC supplies. Okay, it might be two supplies. Exactly the same scenario in today's lab. Right? Yeah, op-amp requires positive and negative two power supplies. Okay, so it does require DC supply. But in transistor circuit, we might just use one DC supply. That might be enough. Besides of the DC supply, we also have an AC input source, VI. Remember in today's lab? Okay, so we always have DC supply and AC input. Therefore, two independent sources. We need to conduct the analysis separately, right? Separately. One source at a time. Okay, one DC supply at a time. That's why two sources, maybe more than two. But when you have positive and negative DC supplies, we can do the DC analysis one time to cover both positive and negative supplies. Okay, that's why we always gonna still have two analysis. One is DC, including might only one DC supply or maybe two. The other is the AC analysis. Okay, so two. The principle behind this is what? Just a superposition, right? You have two independent sources, and then you can conduct them individually and separately. And the final total result is the sum of the result from each one of them, right? And what DC analysis for and what AC analysis for? in the circuit analysis, remember, the DC analysis is trying to set up so-called operation point, the Q point. I don't know if this concept you guys never heard before. Operation Q point. Okay. Q point is the operation point you can set up, you can place your transistor at into the IV curve. Remember, the IV curve is looks like this way. ID versus VDS, and then IV curve looks like this, right? This, of course, these are multiple IV curve corresponding to different VGS. There are different VGS. DC analysis can locate your operation point in here, here, or here, right? Anywhere, depending upon your DC circuit, depending upon your DC analysis result. Okay. And from here, we can also say I'm sketching the what? Boundary, two boundaries to separate the entire IV curve into 3 different regions. So among this operation 1 through 3, which one is for our amplifier application? Anyone remember? Among operation point 1 through 3, which one is very good? 2 is right. Okay. This is the amplifier. In other words, your DC circuit, good, Kevin is right too. Okay. So in your DC circuit, you got to make sure your operation point, which is the result of the DC circuit, is located into this, what? Saturation region, right? If it is falling to 3, this is cut-off region. Guess what? No current, nothing happened. This is still off. This transistor is still off. It doesn't work at all. And if you somehow DC circuit making your operation point Q point is located in this non-saturation region, this is not what? Not amplifier. This is switching. Remember 2 applications? Switching and amplification. You also call amplification as the continuous control, right? So your DC analysis is for what? For locating your operation point into the proper IV curve operation region. For amplification application, you have to make sure your operation point is in the saturation region. Just simple like that. Who can guarantee that? Your DC circuit, okay, your DC circuit design, or say. That's what the DC analysis for. Okay. And what AC analysis for? Find AC gain. Because don't forget that you have AC input, VI. Then you have DC supply. And you got the output. Right? What's the circuit in the middle? We don't need to worry about for now. Basic configuration is just like this is a transistor circuit. Okay, transistor circuit. Right? AC input, DC supply. Of course, as we just discussed, they are the reason why we are conducting DC and AC small signal analysis, right? But just that your output is trying to amplify what? Because it's the transistor amplifying the circuit, right? Amplifier. Circuit, right? amplifier circuit is trying to amplify what? Amplifying AC, okay, which is this guy. You're not amplifying DC, okay. DC is just to locate your operation point. You're not amplifying this DC. So output, of course, containing a DC result and an AC result. However, that AC result divided by the AC input is the gain, or say the AC gain. This is our AC small signal analysis for. Find this gain. So once again, DC is responsible of locating your operation point into the proper region. For AC analysis is for finding the AC gain. You're amplifying the AC input. You're not amplifying the DC supply. Your output AC magnitude divided by the input AC small signal magnitude equals to the gain. For AC analysis, just trying to take care of this gain, find this gain. Does the concept make sense? Right. And the DC analysis, of course, what does it mean by locating your Q point, operation point? But just to decide what is the DC current, DC voltage are. In the circuit analysis, or say the problem, you're looking for what? DC in current, a DC voltage across drain and source, and the DC voltage across gate and source. Okay. ID, VDS, VGS, three things. Okay. The results of DC analysis. Small signal analysis, you're looking for the A sub V, the gain. These are the idea and the concept. If they are clear, then we can go ahead. Talk about DC analysis. Let's talk about DC analysis, and followed by AC, of course. First of all, you need to understand there are three MOSFET circuit configurations. Yeah, three: SCD and CG. For second letters, S, D, and G, of course, very meaningful. They're representing respectively three terminals: source, drain, and gate. However, the first word C represents what? Common. It's a word common. How to understand this common? Okay. This is very important. This is very important. Okay. What does it mean by common source, or common drain, or common gate? Right. Okay. You need to understand how to identify this common what circuit. See what does it mean by common. So listen carefully. Common means this. Okay, look at this particular circuit here. Okay, a MOSFET circuit, and we can tell this terminal is the drain. This terminal is the source. This terminal is the gate. No problem. Okay, no problem. This gate. And we are seeing that your input definitely is somehow reaching one of them, right? The input is going either G or D or S, right? And how about output? Output is out of one of them as well. So input is giving to gate. Output is out of the drain. The left terminal, S, source, is the common terminal. Did I make myself clear? It's a common terminal for both input and output. That's why this is what? Common source circuit. It's a common source circuit. Because once again, input is occupying gate. Output is occupied by the drain. And the left circuit here is a common circuit and the common terminal. So this is called common dot terminal. Be very careful, okay? The common terminal is not necessarily a ground. It's not necessary, okay? So you are not looking for the ground for the common terminal. No, it's not necessary. It's not necessary that way. Instead, you're looking for the input and then followed by output. And then the left one is the common terminal. Here is repeating that. Input, gate, output, drain. The common terminal is the source, the left one. And also here is emphasizing once again, your DC supply is required to provide bias voltage and current. In other words, just locating your operation point into the saturation region so that you're able to work as an amplifier. Otherwise, you are nothing more than a switch. Does it make sense? This is saturation region. Blue point here, amplifier. This is the non-saturation region. The Q point is here, it's a switch. If you fall into even the down here, the cutoff region, well, it's off. You're gonna do nothing. And a little bit more detail. Okay, so first of all, sometimes you can see a capacitor after the input AC PI. This capacitor is trying to couple the AC and AC because if any DC in front of it, it cannot pass through. Okay. So this capacitor here is guaranteed that the input signal here to the gate is purely AC. Okay. This is what this capacitor for. And therefore, anyone knows what does it mean by C sub C? This subscript C is representing what word? Anyone, any experience? C sub C is what? What capacitor? What's the name? Common? No, it's actually coupling. It's coupling. It's coupling capacitor because it is located at the input, so it's called input coupling capacitor. Input coupling capacitor. You might be able to see it at the output too, okay, which is output coupling. Both are for blocking the DC, blocking the possible DC. Okay. A coupling capacitor, C sub C. And the DC analysis results, once again, looking for these three guys. Once again, looking for these three guys. Has nothing to do with the AC input. Of course, this is a superposition principle. When you conduct a DC analysis, you need to get rid of the AC source. That makes sense. And of course, never forget, the circuit voltage or current is always equals to the total result from DC and AC analysis. However, this is not something we really gonna use a lot. No, we are not looking for the output voltage. Three guys and AC gain rather than output signal. Okay, keep this concept strong as possible, because probably we haven't yet established such a kind of concept. We don't care the inputs, we don't care the output either. We care about the gain of a system or circuit. Just like what we did today, we are emphasizing what that the gain must be 10. As to the output, what is it? Well, the output is input dependent. It's up to your input. We just take care of the gain. It also makes perfect sense. imagine you're designing an amplifier. Then what's the requirement for the amplifier from the customer? Have you ever think about this? I'm paying you, ask you to design or make a amplifier for me, right? And what the requirement I can give you? Gain, okay, rather than certain output. Why is that? Anyone knows why is that?
Because your inputs might vary.
Exactly, very good. Exactly. As an engineer, we are paid to build a amplifier. Okay, we just take care of the gain. As to the input, but it's out of our control, right? But the customer input whatever they want. It's not up to us. Therefore, the output is not up to us either. Does it make sense? We only take care of the gain. All right. So this is the very strong concept you need to establish, okay, to amplifier, to any amplification product. You need to understand this. Okay, you are implementing the gain, and the gain only. Somehow you guarantee the gain is certain value with maybe certain percentage of the tolerance of error, and then to any kind of input. I give you input of 1 volt or 10 volts, your remains as same as required. Okay, so be aware of this. Okay, it's not the output. No. We don't care. That's absolutely up to a particular input out of our control. Okay? We just worry about the gain. That's why I gave a cross here. Okay, so this principle, of course, is correct. Don't take me wrong. Okay, don't take me wrong. We are not worrying about the output signal. Looking for the gain, AC gain. Obviously, this is something you want to print it out, okay, as one of your handouts by your hand all the time, right? Because this is a very detailed procedure for DC analysis of MOSFET circuits. Okay. Let's go over them to see what it's about. So how to conduct the DC analysis. Okay. First, you need to find a DC circuit. How to find a DC circuit. This is based on, once again, the superposition principle. To keep the DC supply, right? You keep the DC supply. However, you need to get rid of the rest of the independent source, which is AC source. Right? And also, if you see any capacitor, what do you do? Open them. In DC circuit, capacitor is open circuit. Inductor is short circuit, right? This is how you end up with a DC circuit. Of course, the first step, right? Based on which we start to do circuit analysis. This is once again 235 knowledge. Okay. You need to apply KCL, KVL, voltage divider, current divider, maybe. And keep in mind that we are looking for these 3 guys. And you also need to be careful that VGS and VSG, what's the difference? I mean, why we have 2?
Isn't one for the P type and one's for the N type?
That's exactly right. Okay, one is N channel and another is P channel. So this is for what? Which one? This is for what? N channel. This is for P. Same thing here. VS is N, VSD is for P. ID, of course, is same for both. So keep in mind you're looking for these 3 things. keep in mind you're looking for these three things, and then start to conduct circuit analysis. Basically, you need equations to find unknowns, right? So I'm providing you some idea about how to come up with the equations. First equation you don't want to lose, okay, very important, is the saturation operation ID current equation. Here, I'm emphasizing. At the beginning, you need to assume, just like in diode, you know it's on or off by watching the circuit. Most of the time, you don't know. At least you're not sure, right? So what we did, assume it is on, and then applied our model, right? In diode. Here, similar. Of course, at the beginning, you have no idea about this is saturation or non-saturation. Of course, you don't know yet. That decision, that conclusion is all up to your DC result. You just started. Of course, you don't have any result. So at the beginning, you need to assume it's a saturation operation. And then go back to check your result to confirm it's right or wrong, okay? Same logic as in the diode circuit, okay? At the beginning, you have no idea, okay? Assume it's a saturation operation, okay? And then you immediately have a saturation current for a drain current equation. Where is it? Previous lecture slides, page 8 and page 12. Why we have 2 pages? Anyone knows? Anyone, any memory? Why we have 2 pages? Oh, without going back to check your slides. What do you think?
Is it because there's a p-channel equation? And
exactly. Page 8 is for N channel. Page 12 is for P channel. Okay. Of course, you have 2 pages. Okay. That's fine. That's one equation. Immediately, you have one equation. Immediately, you have one equation there. And then these 2 are also very useful, very simple, and very useful. What they're saying is drain current is equal to source current. What does it mean by this? Drain source gate, right? If you're talking about the drain current is downwards, obviously, ID. What's the source current? Downwards too, IS. To MOSFET this particular type of transistor, ID equals IS. Okay. And what else? It also say IG is 0. What does it mean by IG? IG is this current. IG is 0. This is a big deal. This is a big deal. Your IG is equals 0 means what? Anyone? IG is 0 means what? Doesn't mean anything to you? As an electrical engineer, you should immediately come up with a conclusion safely. Gate current 0 means what? What about the gate? We should be
closed.
It's open. Very good.
Sorry.
Open circuit. That's okay. I think you mean the same, but we don't say it closed. Okay, closed is not obviously not electrical engineers. We are professional electrical engineers, so we should come up with something more accurate or more professional. 0 current immediately and safely, we can have a conclusion. It's open circuit. It's a big deal. Your gate is open circuit to the rest of the part of the transistor. It's a little bit hard to believe, but it is true. Okay, it's an open circuit. It's a very big deal. Well, if this is open circuit, then what is the gate for then? It's useless, isn't it? Of course not. Of course not. And how gates can contribute then? How can gate contribute to the transistor? Anyone? Any idea? It's already open. It's open. Then what can you do then? Anything? Any comments?
If you vary the voltage on it, then it controls the.
Very good. Very good. Connor is exactly right. Okay. Connor is exactly right. Your open circuit. Well, so what? I have voltage. Remember, you have VGS, which is controlling the IV curve. Remember? I just mentioned here. Your VGS. Different VGS, you have different IV curve. Okay. So this is once again in the midterm one. Obviously, we also had a couple of multiple choice questions asking for the short circuit and open circuit concept. Right. It's a very basic. We need to be very sensitive to these things. Okay, be sensitive to these things. Zero current. Okay, that's open circuit. However, open circuit doesn't mean it's not contributing anything. It doesn't mean it cannot do anything. It can have voltage, which also significant. Okay. This is the next equation we need. Gate open, string current equals source current, and one ID equation over there. These are all useful. And then next, you need to do what? Now is the time for KVL or KCL. Time for a KVL and KCL. You might also thinking of the voltage divider gate at the gates, VDC. It's all up to the given specific circuit about what you can do. Okay, it's not something it's fixed. Okay. After using these three equations, you start just thinking of the KVL or KCL. And also you need a VGS or VSG loop KVL. You need this equation too. Last but not least, from the top to bottom, pass KVL, you need that too. So these are pretty much, I'm listing the possible equations you might want. So given the circuit, by applying the weapons listed here, it should be sufficient for you to solve a circuit, solve any circuit actually. So this is what? Arsenal, right? It's absolutely arsenal. Enough for you to defend yourself from any problem attack. This energy fit scenario, I think so. This is really awesome. It's absolutely enough. Absolutely enough. Just keep thinking, using them. Okay, you don't want to have this arsenal. However, you never use them. That's wasting. That's absolutely wasting. These should be enough for you to conduct the DC analysis so that you can find VGS, VDS, and ID. Okay, by examples, of course, we will see how to use them more. After finding them is not done. Okay, always remember, after finding them is not done yet. Why is not done? because these results are based on assumption at the beginning, which not been verified yet. You need to justify your assumption, and then you can say, okay, these are correct values, correct results. Does that make sense? You don't know if your assumption is right or wrong yet, and then you can't use those results. That's why you need to check. And this is the next step. Check what? Check the relationship between the VDS and the VDS saturation boundary. What does this mean? This means this. Okay. Going back to this IV curve. Okay, at the beginning, you're assuming the saturation region. That's why you got the saturation current equation, right? And then you calculate ID, VGS, VDS. And then you need to verify the saturation assumption, right or wrong. How to verify that? You need to, because you calculate the VDS from here, right? To here, your VDS has a what? VDS saturation boundary voltage. If your resulted VDS here, from here, based on this assumption, is what? Greater than that. What's your conclusion? If your VDS here is greater than this VDS saturation here, what's the conclusion?
You're in the saturation region?
Exactly, which means your assumption was correct. Which means your assumption of saturation region was correct. Because you see, your VDS is turned out to be here or here or here, right side of the saturation boundary. Of course, is inside of here. Right? If otherwise, VDS is less than the VDS saturation region, what does it mean? It's here, here, or here. That means what? Your assumption at the beginning was wrong. It is not in the saturation region at all. Because your result of VDS is not fitting the saturation region requirement. Because saturation region means your VDS is greater than the VDS saturation. Now your result of VDS is not greater, it's smaller. Your assumption was wrong. The assumption is wrong means what? It is in non-saturation region. This is the case. Non-saturation is the. Then what? Here, A. You need to compare. Okay, VDS compare with the VDS saturation. How to find the VDS saturation boundary, which means how to find this voltage. You have a formula. Okay? You understand you have formula. Where is the formula? Previous lecture slides again. Page 7 and 11. Why 2 pages? One for N channel, the other for P channel, right? You have an equation to calculate the saturation voltage. Saturation voltage. And to compare, if the saturation assumption is right, and what? Hooray, right? We should say hooray, we're done. This saturation region and the calculated VDS, VGS, and ID from a previous step here are valid. And since it is in saturation region, we are ready to do the AC small signal analysis as well. But if it's not right, like I said, in the non-saturation region, you need to go back to what? Go back to page 8 and 12 to find the non-saturation current ID equation. Well, first, let me pull up the previous lecture so you understand better what I'm saying here. First, page 8. This is page 8. Can you see these two equations? One for saturation, the other is for non-saturation. At the beginning, you assume saturation, so you use the second one. And if afterwards it turned out to be wrong, then you go back to use the first one here. Of course, this is the N channel. You go to page 12 for P channel. Equations. Here. And page 7 means this page. This is what? Saturation boundary formula. The boundary is boundary. You need to use this equation to calculate what is this boundary, and then use your VDS to compare with it. And page 11 means this equation for P channel, right? Does everything make sense so far? Any questions? Any questions? So once you use the non-saturation region equation, well, the first we need to understand is it actually cannot work as amplifier, not anymore. No AC analysis is needed. Does that make sense? No AC. Because it doesn't even work. But if you still need to find out the correct VGS, VDS, and ID value, you need to do the circuit analysis all over again because you have a new different equation. You need to do the algebra all over again. Okay, this is the DC analysis procedure here. DC analysis procedure here. All right. If this makes sense, then let's just go over examples to see how we really use it. First example, let's see how we do this. Okay, how we do this. MOSFET circuit, and we have a bunch of resistors R1, R2, RD. And the DC supply on top 5 volt. VTN, the threshold voltage for N channel is 1 volt. Anyone knows what we are using this VTN for? Where are we going to use it? This guy. Anyone notice?
Our amperage equation for ID.
Very good. That's a very good memory. ID, we're going to use it. Anyone else? Here. Okay, here. Let me show you. When you look for the boundary, you see it? VGS is something you already obtained. The VTN is something given. On the boundary,
We lost your audio again.
How about now?
Yep, that's good.
All right. I just refresh it. No, just refresh it, obviously. Where are we at?
I think right when you switched from the PowerPoint back to your paper, maybe.
Okay. So VTN, once again, let me summarize what I have just said, which you guys didn't hear. VTN will be used for ID saturation equation and also to find the BDS saturation boundary. Those two formulas, which should be on your sheet for future exam. Okay, feel free to copy. Okay, but you need to have them ready there. Okay, and then you're gonna apply the VTN. The KN here is the parameter used for what? For looking for the ID saturation current too. Okay, so I think so I'm gonna do examples next lecture and the following lectures too. So I suggest you to print out those equations as your handout. Okay, put them out as your handout. So when the in-class exercise, you can do it by yourself. Okay, you can do it right. And then just to conduct a DC analysis to find those three guys. 1, 2, 3, 2 voltages, 1 current. So if you look at the procedure here, what you see here is the first step, find a DC circuit. Right? Find a DC circuit. So to this guy, how to find a DC circuit? Open capacitor. Get rid of the AC source by short it out. And this is a voltage source, short it out. So the rest of the DC circuit, the left DC circuit, looks like this, right? Does it make sense? This is the first step. You obtain the correct DC circuit. Capacitor, get rid of the AC source, and then here, whatever left is DC circuit. Okay. Then once again, go back to the procedure here. Start to find them. At the beginning, I'm assuming the saturation operation region. So immediately I go to that handout to copy that equation. Right? To copy that equation. That equation is here. Page 8. No, page 8 here. This equation, does it make sense? This one. Kn is here, given. VTN here, given. So in this equation, you have ID and the VGS, 2 unknowns. Right? We have multiple unknowns, but we have multiple equations too, so don't worry. Right? Of course, this is a quadratic equation, so in terms of algebra, you're expecting to receive what? 2 solutions, right? 2 roots. So you use this equation. And then you have these 2 equations. And the more here, you need to consider a voltage divider at the gate, a VGS loop KVL, and from top to bottom pass KVL. 3 things, 3 equations. Let's see. First, ID saturation equation. Okay. Second, this is what? This equation is what? It's a voltage divider. Whatever. Voltage divider means your R1, R2 are sharing VDD. Okay? It's connected. Because here, open. Remember, we just mentioned this is the open circuit. Here is nothing. So R1, R2, they're series connected and they share the total VD voltage from the top to bottom. Does it make sense? So we can apply voltage divider to find the voltage VG here with respect to where? Ground. So from G with respect to the ground is also the voltage across R2. That's why the numerator is R2. Okay. So remember this voltage divider. Voltage divider is total voltage times a rate. The denominator is sum of two branch resistance. The numerator is the voltage. The numerator is the resistance. We are looking voltage for. Voltage divider. If you don't like it, you can also write what? From top VD to the bottom along this path KVL, right? Path KVL also works. VDD minus 0 equal what? R1 times I1 plus R2 times what? Same I1, right? Because once again, this is an open circuit. There's no current here. So current here equals current here. R1's current equals to R2 current. Does it make sense? So either way, the voltage divider will be easier to understand. So voltage divider to find the voltage at the gate with respect to the ground, of course, which is also the voltage across R2. And then according to the handout, remember we need more KVL, KCL. Another option provided is the VGS loop KVL. What does it mean by VGS loop KVL? We erase these things. VGS KVL. First of all, you need to find the loop. The loop is here. VGS loop means the loop containing VGS. Not up here, okay? This loop containing what? R1, RD, and whom? VDG. Remember what I said? We never study VDG. Okay, I mentioned this last lecture. We never study VDG. Okay. We're looking for the VGS loop, so containing VGS. How to write this KVL? I don't know if this makes sense. In this KVL, very straightforward. You only have two voltage involved in this loop. One is voltage cross R2. The other is the VGS. Only two voltages. No more, no less. Right? Voltage cross R2 is nothing but VG. So VG equals to VGS. The last one is the from the top to bottom KVL. Be careful. This means the path from here, the VD top DC goes through VDS and all the way down to the bottom, which is ground. So VDD minus 0 is equal to the current through RD times RD plus the voltage drop between drain and the source. So once again, VDD minus 0 equals to IDRD plus VDS. Of course, if you move VDS to the other side, you end up with this equation. Same equation. Does it make sense? Any questions? These equations, of course, enough to find all of those. We had a homework problem similar. So, but I want to ask you guys one more time. From this circuit, let me ask you: is this current same as current here? The same?
No.
Absolutely not. Okay. No way to be true, because I remember there were a couple of students messed this up. These two are absolutely not same current. Okay, absolutely not. But not only because they are in opposite direction. It's not saying that current, say I1. This is ID, right? I1 equal to negative ID? No. Absolutely not. Okay. Because I remember a couple of students make a mistake saying inside of this loop, of course, in the loop, it seems the current here equals the current here. No. It's absolutely not right. Okay. Don't keep this wrong concept. It's one of the homework problem. You have a power supply here, say V5 volts. And you have a resistor here. You have a resistor here. And we can skip the transistor here. Say this is ID, this is I1. How to analyze this circuit? If you cannot see this, I can equivalent it to be what? This 5 volts equivalent to this case. Therefore, what can you do? Can you see it? This is the equivalent circuit. From here, you can easily tell this current is absolutely not equal to this current. Does it make sense now? Or if you more comfortable, okay, let me reverse the current direction. If you do the mesh in here, I1 equals to ID, no way, right? Why is that? I1 here is affected by the mesh current here too. So the true current here is equals to what? Equals to I1 equals to what? ID, if we call it I2 minus I2. Does it make sense? Can you guys hear me?
Yep.
All right. So when you see a power supply on top, this side current is absolutely not same as this side current. Because if we do a equivalent circuit like this, you will be able to see that. They're in different mesh. Okay, they're in different mesh current. And that's why. Same back in here. The current here is absolutely not same as current here. Okay, absolutely not. Absolutely not.
Hey, Dr. Zoll, I got another question.
Yeah, sure, go ahead.
Okay, so the VDS voltage, so as you increase the gate voltage and the whole curve of the transistor kind of moves up. So eventually when your current increases enough, it would like
Your current increased enough. What do you mean? The ID
Um,
current?
the ID would increase enough where the voltage across the resistor was quite a bit, and then the VDS would be like a lot less, I guess, because like the VDS equals the VDD minus RD. So when RD is equals close to the source, then
ID.
will you fall back into like the non-saturation region eventually?
Increase your current a lot, and then
Yeah. So
your system originally is in the saturation region, right?
yeah,
And then
originally.
you increase your current a lot.
Mm-hmm.
You won't be able to increase your current a lot. You need to understand this because remember the IV curve, the slope is very flat. You need to increase the VDS a lot, really, really a lot, to increase a little bit to ID.
Yes. Yeah.
So you won't be able to increase ID a lot, make it squeezing the VDS back to the non-saturation region. No, that won't happen.
Yeah. I mean, when the when you like open up the transistor more and the VDS starts to get smaller because it's dropping more voltage across that RD, and the
how would that happen? I mean, your ID won't increase a lot. No, it's still under control of the transistor behavior.
yes, and when the transistor turns on more, like the VGS increases from the AC or whatever. Then the VDS would start to get smaller because it's dropping.
That's right.
Yeah.
You're talking about AC. I'm sorry. I thought you were talking about DC. Yes, you're talking about AC, right? AC is swinging there. Yes.
Yeah, because the VDS would decrease as you increase VGS, right?
Correct.
Okay, that's all. Okay,
and don't worry about going back to the DC. Yeah. The reason I thought you were talking about DC is you at the beginning you worry about it goes back to the non-saturation region. No.
Yeah.
Because AC swinging won't push your operation point back to the non-saturation region. That's not possible.
Okay.
Yeah, that won't push your operation region operation point back to the non-saturation. No, that won't happen. That won't happen.
Okay. Got you.
And the your VGS, of course, determining how much you can swing in AC.
Mm-hmm.
That's true. Okay, that's true.
Yeah. Okay. Thank you, Dr. Zoe.
Sure, no problem. All right. So going back to this calculation, so after we get these three values, what's the next? And anyone remember? What's the next to do?
We have to check the relationship.
Great. Very good. Very good. Yep. Chat. 2 got it too. Yeah, 2 remember. You gotta chat. So first, checking means what? Checking means you compare your VDS with VDS saturation boundary. Right? So you got a VDS value here. From this calculation, you got VDS 3 volts, VGS 2 volts. Keep them in mind. And then VDS 3 volts compared with VDS saturation voltage. This formula is once again available from page 7 for N channel, page 11 for P channel. Your VGS is what? 2, we just mentioned. Minus given VTN, which is 1. So boundary voltage for VDS saturation is what? 1 volt. What's the conclusion here?
The assumption is correct.
Here we go. Then what? Done. Okay, you should hooray. Does this make sense? Does everything make sense so far?
Yep. And if we were
Good.
doing a full AC or a full analysis, we would move on to AC after that, right?
Exactly. So it is not hard to imagine if, as you said, if we do full analysis, we need to do AC. But to do AC, we need what? DC results. Remember, in the diode circuit. Same idea here. The DC analysis always goes first. Because your AC analysis requires a DC analysis result. Just like the discussion we just had with Connor. How much swing how much AC gain you can obtain is up to your DC operation point, where you're located at. Absolutely matter. So this is example 1. Okay, following once again this procedure, you should not be far away from here. You should not be far away from the. You shouldn't get on the wrong track. Okay, and also remember these options. Okay, these weapons, different weapons. One doesn't work. One is not enough. Okay, you have more. Okay, remember using this arsenal. If this is fine, then let's take a look at the example 2. Example 2. Example 2, we're seeing similar circuit. However, at the beginning, you need to be very careful. Okay, so this is the gate, right? This is the gate. Very easy. Well, this is what? It's not drain anymore. This is source. Okay. This is what? This is a drain. Right? Does it make sense? And therefore, this is an N channel or P channel. Of course, this matters.
It's a P channel.
It's absolutely a P channel. Okay, this is the P channel. Because this result is determining what formula we should use. Okay, of course, it matters. It matters. Okay. So DC circuit, first step is what? Open here, short here. Here we go. Right, here we go. P channel, assuming is assumption, as assuming is the saturation, and then we go to what? Page 12, right? Here, P channel. This equation, does it make sense? So you got to make sure you're applying the correct formula, right? ID here, Kp times VSG plus ETP. This equation we definitely use. P channel, saturation. And we know ID equals to IS. Okay, it's already labeled here. ID equals to IS. So here is open circuit, very nice. And then when we start to think, VSG voltage loop KBL, right? VSG loop, okay, it's not VGS because there's a P channel. Where is VSG loop KBL? Where is this loop? Up here, right? Does it make sense? You need to have the loop containing VSG. Okay? So it's not like try to memorize the location. Right? Loop containing VSG, not the loop down here, right? So I'll give you guys 1 minute to write this VSG loop KBL yourself. What is it? Go ahead. 1 minute for this KVL, and another minute is for what? Voltage divider. R1 and R2 voltage divider. Two equations. Go ahead. Try it yourself. Once again, one is voltage divider, R1, R2. The other is the ESG loop KVL. One more minute. All right, let's see these two equations, voltage divider and VSG loop KVL. Take a look at the solution here and compare with yours. See any questions here? Any questions? Do they make sense? Any thoughts? All right, thank you, Shane. So basically, once again, if you're looking for the voltage at the gate, it means once again, from the gate towards the ground, right? So voltage across R2. We got this VG by this voltage divider. However, that's once again the voltage from here to the ground. So see here, okay. What we need for the later KVL in the top loop is the voltage here, the voltage across R1, rather than VG. So what do you do? How to find a voltage across R1? You need to use the voltage at this terminal of R1 minus the voltage at this terminal of the R1. So at this terminal, the voltage is VDD. This terminal is VG. We just find that. So VDD minus VG is equal to the voltage across R1 with this polarity. It equals to VSG. So this is the KVL in the VSG loop. Okay. And if this makes sense, and I'll give you guys another 2 minutes to write from the top to bottom KVL, past KVL. All right, this pause KVO should not be very difficult, right? So from top to bottom, we're going through a short circuit, and there's no voltage drop here. So you go through a BSD, 1 voltage. Second voltage is a voltage across RD equals to ID times RD. So sum of these two equals to VDD minus 0. Any questions regarding the equations? To be honest, I don't remember what is the correct answer, but if this equation makes sense, then you can go ahead to calculate them. Yep, BSD equals to 0.665. And then what do we need to do? We need to check. I leave the checking part of the work for you to do after the class as an exercise. Next lecture, I'm gonna show the solution about the check, and you can also tell me what you found from that checking. Okay. So that's all for today, and thank you for attending today's lecture. And the next lecture, we will review the midterm 1. I'm in the middle of the grading, so by next Tuesday, I think I will be ready for reviewing it. Okay. All right, thank you again, and talk to you guys next week. You too. Thank you, Daniel. Bye-bye.